All right, today we are going to discuss Newton's second law. Remember, Newton's first law was any object in motion wants to stay in motion, and any object at rest wants to stay at rest unless acted upon by an outside force. Well, Newton's second law, first of all, there's a couple of terms here that are important. Mass and weight. Okay, so a mass is how much matter there is in an object. The weight is the force of gravity acting on the object. So a lot of times we treat those as interchangeable terms, mass and weight, but they are different. Okay, so we all have an amount of mass, which basically an amount of atoms in us. Okay, now that's not going to change no matter where we go. However, our weight can change. So like me, if I weigh a certain amount, let's say I weigh 250 pounds on Earth, okay, I have so many atoms in me, okay, making up my bones and muscles and fat and all that stuff. Okay, well, if I go to the moon, my mass is not going to change, but my weight is. Okay, the moon's gravity is much less than Earth's, so I'm going to weigh less on Earth. I don't know exactly what, but it's going to be quite a bit less. But my mass isn't changing. No one, I didn't get rid of any atoms or cells or anything like that. I still have all of that. I just the force of gravity on the moon is different. So my mass wouldn't change, but my weight could. If I decide to go on a diet and lose 20 pounds, okay, my weight is changing, but so is my mass because I'm having less. I'm getting rid of cells. I'm getting rid of matter. I'm getting rid of fat. So they are kind of similar, but and we use them a lot similarly, but they're not completely similar. Mass and weight. So Newton's second law. A net force acting on an object causes the object to accelerate in the direction of the force. Okay. The acceleration is determined by two factors. So basically what this is saying is if I put a net force on something, it's going to move in that way. Okay, so if my car is stuck in the ditch, okay, and someone stops and helps me push it out, okay, if we're pushing it east, okay, we want it to go east. We're applying a force on that car, and we want that car to continue in the direction that we're pushing it. Okay, if you're playing kickball in Mr. Grady's class, okay, when someone pitches the ball to you, okay, and you kick it in mat ball, you kick it, you're expecting that ball to go in the direction that you swung your foot, that the force that's acting on it. You don't want it to go, the complete opposite direction. You're aiming to kick it a certain way by applying a force to it. So a net force causing an object, acting on an object, causes it to accelerate in that way. There are a couple factors that help determine this. Hang on. Size of the force and the mass of the object. Okay, so it all depends on, first of all, how much force do you put on the object. If my car is in the ditch and I push it with one finger, okay, odds are I'm not going to move that car. Okay, now if me and two other people are pushing that car, okay, we're applying more force to that car, and the odds of us getting out of the ditch are probably better. Same with mat ball. Okay, if you want to aim for a home run, okay, you're gonna apply as much force as you possibly can to that ball when you kick it. Okay, you're gonna increase the force, hoping that you kick it far and it gets a home run. Okay, if you barely put any force to it, okay, you might just get a little bunt, and you'll get to first base, and that'll be about it. Okay, so the size of the force is a huge factor, and then the mass of the object. Okay, if I'm driving my wife's little Honda Insight and it gets stuck in the ditch, that's going to be a lot easier to push out than my Ford F-150, okay? Because that car is much smaller. It has much less mass. So we should be able to push it easier, okay? Now, you guys are used to playing mat ball with a kickball, okay? Well, imagine if you traded that for a bowling ball and you played mat ball with a bowling ball, okay? Now, there would be some people with some broken toes and whatever, but that bowling ball is much heavier. It has a much bigger mass. So if you kicked it as hard as you could, it still probably wouldn't go very far because it has such a big mass. So there's two factors that determine acceleration. That is size of the force and the mass of the object. So heavier, more massive objects require more force. Okay, so this is really obvious in vehicles. Okay, if I'm driving a giant semi truck loaded down with cattle, and someone in front of me hits the brakes, okay, if I slam on the brakes, I'm not going to stop very fast because I have a lot of mass, and it's going to take a lot of force to slow down that mass. Okay. Meanwhile, if I have my wife's little car, it'll stop a lot faster because its mass is much less. It also heavier objects require more force. It's also, I don't know how many of you guys watch a lot of sports, but like it's much easier. If I'm a big football fan, it's much more common for a running back who's really quick to be small than a running back who's big and really quick. It's really rare to be big and quick because if I'm going to quickly change direction, it's easier to move a 150-pound body quickly than it is to move a 250-pound body quickly. So it's going to take more force to move that big body. So that's why typically bigger people aren't as fast or as quick, because it takes so much more force to move that bigger body. Objects accelerate in the direction you apply them. So it would be weird if you threw a baseball forward in it and it went the opposite way. Acceleration is directly proportionate to the force. So basically, if you want a baseball to go harder or farther, you put more force on it. Acceleration is inversely proportionate to the mass. So basically, the smaller it is, the easier it is to accelerate. We'll get into this a little bit in future here. Force equals mass times acceleration. Okay, so force is often in newtons. Mass would be in like kilograms or grams, and then acceleration, remember, is often meters per second. May the force be with you. I think this all should cover it. So tomorrow I will have you do a few calculations with this stuff. I think it'll be pretty easy. But Newton's second law calculations, and basically use force times mass equals acceleration. If I can bring it up. Force equals mass times acceleration. So it should be a matter of just multiplying. So if you have any questions, let me know. You can always email me. we're going to end with this right here. Maybe you've seen this before.
To be an NFL kicker takes more than just nerves of steel and a strong leg. It also requires help from one of the key laws of physics.
It's easy to say, well, I just kicked the ball. Well, let's delve into it. Let's look at the specifics. What actually happens when you kick the ball, and why does the ball go where you ask it to go? And it is Newton's second law of motion.
The second law is one of three laws described in 1687 by Sir Isaac Newton, who used them to describe how and why objects move.
So the second law says, if you have an object with a mass that is accelerating, and acceleration means a change in velocity, that is equal to the amount of force applied to the object. The way we say it with words is F is equal ma.
This also means that in order for an object like a football to accelerate, a force must be applied. To illustrate Newton's second law in kicking, we asked Morten Andersen, the NFL's all-time scoring leader, to perform his craft in front of a high-speed phantom camera. The entire procedure unfolds in less than a second and a half, from snap to hold to kick.
It's all about training and rehearsing and doing something over and over and over again.
To reduce the chance of a block, NFL kickers take just 3 steps to the ball. The final step is with the plant foot, which provides the stable platform for the kick.
I call it the moment of truth, and the moment of truth is basically when your plant foot hits the ground next to the ball. You're either in the right position or the wrong position.
The kick itself involves the entire leg building the force necessary to launch the football.
It's a hammer, and you're swinging the hammer, and you're trusting it, and it's going to be, impacting the ball with great velocity.
An NFL kicker's foot is in contact with the ball for just 8/1000ths of a second, and in that time, his foot applies up to a ton of force to the ball. This quick, violent strike is a perfect example of what's known in physics as an impulse.
Impulse is an important concept because there is a finite time over which the foot is in contact with the ball, and during that time there's a force applied to the football.
An impulse is equal to the force multiplied by the time the force is applied, represented by delta T. If force is graphed versus time, it's possible to see how a larger force or a longer time for the force supplies a bigger impulse.
Since impulse is really just the change in momentum, and since a ball doesn't change its mass, we're really just talking about the change in the speed. The bigger the impulse, the bigger the change in speed, which means the faster the ball is moving after it leaves the kicker's foot.
Ironically, Andersen says the distance of the field goal doesn't change his approach to the kick itself.
Mentally, you want to look at a 50-plus yarder, like a 40-some yarder, with some room to spare. I think that's a good way to kind of fool yourself into thinking it's a shorter kick.
Whether the kick is short or long, Newton's second law explains what an NFL kicker must do to send a football through the uprights.
All right, we'll call that good.